Well, back, folks, and we're going to be talking today again some more about solutions. I still got my vitamin water, and we're learning about properties of solutions. So what are the solutions' properties as it relates to temperature, as it relates to, I don't think we're going to talk about pressure, but as it relates to a number of things. Another important thing is kind of what dissolves in what. Some things dissolve in some things, and some things don't. And so actually that's where we're going to begin our conversation. So let's get there now. So the properties of a solution. All right, what properties do you have in a solution? All right, very good. All right. The first thing we're going to answer is what will dissolve in what? Not everything dissolves in what. Actually, let me just make a quick highlight. You notice my background image right here is a blue solution. And you can see actually if we pass light through it, it would pass right on through it. So what dissolves what? Well, here's the thing to memorize. Like dissolves like. Yeah, that's right. Like dissolves like. Now, that does not mean blue dissolves a blue and red dissolves red or whatever. It isn't color, but what is it that has to be alike for them to dissolve? It's their polarity. So back in Unit 8, we learned about polarity. There are some things that are polar, and there are things that are not polar, or non-polar, we say. So polar dissolves polar things. So if I take a polar thing and I mix it with another polar thing, it will dissolve. It also dissolves ionic compounds. Polar dissolves ionic compounds, by and large. This is actually, if you recall, from a long time ago, the SAQ table. If it's AQ, it dissolves. If it's S, it doesn't dissolve. And then also, nonpolar things dissolve nonpolar things. However, nonpolar does not dissolve nonpolar. Now, you've had experience with this, so let's take a look on the webcam. So here I have a beaker, and in this beaker I'm going to pour some water. Now, what kind of substance is water? Yeah, it's polar, right? Water is polar, so I've got some water right here. And then to that I want to add some Kairos corn syrup. So I'm going to add some syrup. It's kind of a thick, liquidic type deal, right? Alright, so I've got that added. Now I'm going to take my stirring rod and I'm going to stir it in. Stirry, stirry, stirry. Now let's see how that looks when I zoom it in now. You can kind of see the sugar particles. It's actually kind of a sugar thing. But if I continue to stir it, it essentially is all mixed together. So they dissolve in each other. And so since water is polar, what could you assume about the Karo corn syrup? Now think about it. That's right. It is polar. Well, now let's try something different. Again, I'm going to pour some water into a second beaker. There we go. And then to that, I am going to add another chemical. This one has about the same color as that Karo corn syrup. Now, this particular substance is oil, vegetable oil. All right. Now, if you look carefully now on the screen, what you will see here is there is a separation between the two different substances. There's the oil on the top here, and there's water below here. If I mixed it, let's see what happens. Now, the last one I mixed, and it, of course, dissolved completely. Now, in this particular one, let's zoom in here. What you can see, actually, interestingly enough, is that they stay separated. It's still kind of separating, but there is a distinct line between the water and the oil. And so they are said to not dissolve in each other. That's because, you see, the water is polar and the oil is, well, if it doesn't dissolve, and like dissolves like, that makes the oil, think, think, think. That's correct. It makes it non-polar. So the oil there is non-polar. And if we zoom in just a skosh more, you can kind of see, just a blur is what you can see. oh well, you can see the separation between the two. So what makes the difference is the polarity of the substance. Now, I didn't show an example here, but I can take a nonpolar substance and dissolve a nonpolar substance. An example like that would be oil. What would dissolve the oil? See, gasoline would. Because gasoline is nonpolar. How do I know gasoline is nonpolar? Because if you put it with water, it would separate just like the oil did here in the example I gave just a minute ago. Okay? Now, how does polar dissolve polar? Well, remember in polarity, polar substances, they have little positive ends and negative ends, and essentially, the positive things are attracted to the negative ends of another molecule. So positives are attracted to negatives. So that's why polar dissolves polar. And polar, here's another example of polar. That's not that important. The picture here of water, this is actually an example of what we were just talking about. They've got mercury, carbon tetrachloride, and water, and they separate. And actually, I didn't say this from our example, but the one that's on top is the one that's, we'd say, least dense. Some people say it's not as heavy or something. It actually has to do with the density. Okay? Polar also dissolves ionic, and we already kind of alluded to this. Essentially, the water molecules, they come in here with the sodium, and they come and they surround the sodiums, and they surround them. So this is actually a much better picture than the one you drew a couple of podcasts ago. But it can dissolve ionic. Not all ionic things, but many of them. All right? And, yeah. Nonpolar dissolving nonpolar. Actually, hold on. Nonpolar and polar, the reason they don't separate is the positive things are attracted to the negative things, and they stick together, and the nonpolar things, they stick together, and so they don't dissolve. So this would be basically, it says potassium dichromate. This is water, and this is another nonpolar substance, hexane, and it separates there because the hexane is not attracted to the water molecules. All right. Now, a couple of new definitions. We're into definitions in this unit. There's something called a saturated solution. You might have heard, you ever been saturated, like you're outside in the rain and your clothing got saturated? That means you may as well have taken a shower in your clothes because it's that wet. All right. Saturated means it's the maximum amount of a solute that can dissolve in a solvent. So if I put some green powder or whatever on the bottom of a beaker, after a little bit of time, the beaker becomes a little bit greener, and notice that the pile of green stuff gets smaller. And then I can add a little bit more, or a little bit after a little bit longer, the color becomes greener, and the pile gets a little bit smaller. And if I continue to wait a certain period of time, it's going to stay the same color, and the pile is going to remain the same on the bottom. Why is that? That's because this is saturated. You cannot dissolve anymore. No more green stuff, if you will, can dissolve in the solution. That is the maximum that you can have. Hence, it's said to be saturated. All right? There's also something called solubility. Solubility is the saturation point, if you will. It's the maximum amount that can dissolve. So solubility is actually a number. So, for example, of this particular substance, you could say maybe 85 grams of the stuff, of the green stuff, dissolves in 100 grams of water or something like that. That's actually a number. So the key thing on solubility is it's a number. All right? Whereas saturation, it's just reached the point of saturation. All right. Now you can also have an unsaturated solution. That's less than the maximum. And how can I tell if I have a saturated solution versus an unsaturated solution? In an unsaturated solution, there's no stuff at the bottom. If you look at this green flask or green solution, there's no little particles at the bottom, like green floaties, if you will. So they all dissolved. All right. So if they all dissolve, there are no floaties, then it's said to be unsaturated. All right. A couple other terms, miscible. Miscible means when substances dissolve in each other. So you have two substances that dissolve in each other. They're said to be miscible. So the example from a minute ago was the K-rose syrup and the water. They are miscible in each other. If they are immiscible, then they don't dissolve in each other, and that would be example, of course, the oil and the water. Or here, this is oil and water, and you kind of see a picture right there. That is immiscible. All right. Now, guess what? There's also a function of temperature. So if you are trying to dissolve something, there is a issue with temperature. Okay? So if you have warm water versus cold water, some things will dissolve better. So here we have a solid dissolved in a liquid. In particular, this particular graph is the liquid water. Water is the solvent. And so, for example, I have sodium nitrate. So at 0 degrees, you could dissolve 70 grams of sodium nitrate in water. However, if you were to come up here to 80 degrees Celsius, you could dissolve 150 grams of sodium nitrate in water. So it's a function of temperature. And I want you to notice, generally speaking, with some exceptions, particularly the sulfates, what do you notice about this graph? Generally speaking, the higher the temperature, the higher the solubility. That's the maximum amount that you can reach. Okay? So a general rule for the solubility of solids, as temperature goes up, the solubility goes up. Right? So that's the maximum amount. You go back to our graph, they all go up. This is the only exception right here. The sodium sulfate. Typically the sulfates do weird things where they happen to go down on the graph. Okay? Now, there's a different situation, and I want you to copy this graph, or this is in your packet too, you could cut it out. Actually, what you ought to do is take this, I don't know what page, it'll vary from year to year, but there is these two graphs on there, and you should copy them into your notebook, or just cut them out actually. And so here I have some gases and liquids, but notice this is a gas, so for the solubility as a function of temperature. So notice that basically what happens here, all right, I'll bet you know this. If you take a can of soda, right? Take a can of soda. It's got carbon dioxide in it too, right? What if you were to leave this out overnight? It's going to warm up. And what's going to happen to the carbonation? It's going to go flat. Okay? So if I have a hot can of soda, it's going to have a lower solubility. Does that make sense? So the general rule for solubility of gases, as the temperature goes up, the solubility goes down. It's a reverse deal. Now, an interesting application of this is something called thermal pollution. So if you have a factory or a power plant, this is a power plant, and one of the things that they need, they put power plants near bodies of water, as in this picture. Any ideas why? It's because they need to use the water to cool down their stuff. So if you were to take water from a lake or a stream, and then you use this water to just cool your stuff down, then you can then expel back into the water warm water. Make sense? Duh, right? What's going to happen, even though you put, let's say you use the water and you return it, it's completely safe. You're not adding toxic chemicals or nasty things like that. What you're doing is you're just adding heat to the water. But as you increase the temperature, as we said just a minute ago, the solubility of the gases goes down. What you're going to do is you're going to take all of the dissolved gases in the water out, and it's called thermal pollution. All right, let's illustrate this this way. Let's think of a box. This box is a stream of ocean, a stream of water, pardon me, and I'm going to put in that stream of water a fish. All right, that's a fish. Now, I'll bet you don't know this, but fish need oxygen just like you and me. He's, of course, got gills. There's his gills. But he needs oxygen O2. I think that's actually a misconception. Most people think that the fish breathe in water. If they were in pure water, they would suffocate. They actually breathe oxygen. They extract, maybe is a better word, the oxygen from the water through their gills, the O2. So it's dissolved oxygen that's in the water that they're actually using to live. We breathe in the oxygen. They extract it from as a solution into their gills. Okay, and so they need this oxygen. But if you were to heat up the stream, what would happen to this oxygen is it would leave, just as the soda would become flat. And these guys would say, ah, and they would suffocate and die. So if you go back to our thermal pollution thing, if we were to heat up this water, then all we would do is we would kill all of the fishies because they would have no oxygen to live. They need that oxygen. Another way to look at this, just as a side note, maybe to understand the whole oxygen thing, do you realize in the bottom of most like aquariums, they have a little device in the bottom and it's producing bubbles, the bubbler. It's producing, and what they're trying to do is to add more oxygen because, of course, the fishies are are breathing in the oxygen, that gives them additional oxygen. Now, some fish require more oxygen than others. It's kind of a biological thing. And some as the oxygen molecules from the air strike the water, some of it's dissolved, and that's enough for many fish, but some fish need extras. Now, where do you think you would find the most oxygenated water in the world? First of all, it would have to be cold, because you don't want hot water. And then you'd have to have a way for more oxygen to get into the lakes and streams or wherever. And the answer is, of course, you would have a river, and this is a waterfall. So if you had a waterfall in the extreme northern parts of the world or extreme southern parts, in a very cold region of the world, you'd have very cold water. As it comes down to this body right here, this water here is super oxygenated. It has reached its saturation point. But it would get more of it because, of course, it would be cold. So cold waterfalls have the most oxygen in there. So critters that need more oxygen tend to live there. Those who need less are like in still ponds and stuff like that. So some creatures need that turbulence. The turbulence of the river actually is what gives the water the oxygen. Well, that concludes the podcast. We will see you later on the land of school. Bye.